I also had a question.
Go for
I
it.
had
I
a
went ahead and
question
turned
about
the recording on.
the RC circuit problem in the homework from that was due last night. It was asking like 75% of its maximum value to charge the capacitor. I went through the math and I was finding like 1.8 or something like that, and the thing is telling me 2.01. I went and back engineered that and got like 86.6%. So like root 3/2.
Is that in a
rather
practice
than
or a homework? Is that a practice test or a homework?
that was homework problem 24.46. Sorry,
Right.
26.46.
Take a screenshot for that of that one for me if you don't mind, and email it to me and I'll check and see. There might be an error in the actual grading of that one. So that could be the issue, or it might be asking you for it in terms of its time constant. So you could be, for instance, asked for the number of time constants that have to go by for it, and that's a different unit than if they're asking you for seconds, and that's a different unit if they're asking you for microseconds. That's what I normally find the problem.
So they were asking in units of tau.
Yeah, that's
so
time constants, RC. So it sounds like you did follow it right. So yeah, it might just be an error on their behalf. I will check it for you when you send me that, just so I can have the, because each person, each time you take it's going to have a different number and stuff like that. So
I sent you a feedback in the thing. Do you receive those, or do those just go to your junk mail?
I did hardly ever check them, but they do come to my come to one of my accounts. So yeah, I'd prefer not to send it that way, but I'll go looking for it. Now
I can send a message to you now, or I can share my screen and show you what I'm talking about.
Actually, it'd be better to have a photo of it anyway. So yeah, if you could send it again, that'd be great. But I'll look for it as well, just in case something goes through. Now I'm trying to figure out what the heck's going on here. I need to share with Zoom my privacy stuff, evidently, because it's not letting me share my screen. By the way, I asked Jack, I think it was, to remind me to put the recording on. I did put that back on, so no need to worry about that now. I am looking right now, trying to find access to what I need to share my screen, and it told me a message that I promptly did not read. So I'm going to try to do it again. You know, it's like when you're on the road and you ask somebody for directions, and they like say, you're going to go down here and take a right, and then you like stop listening. Yeah, that's what just happened. So it says open system preferences, security and privacy to grant access. Allow Zoom to share your screen. Okay. So system preferences, security and privacy. Oh, there it is. Security and privacy. And allow share Zoom to share your screen. So let's open this. I'm working on it, folks, here. Okay, App Store, show a message. Oh, yeah, that's not what it's not actually showing me, not showing me anything about allow to share my screen. Maybe it's under screen recording. Okay, so that's not it. It said screen recording, so I had that. Let's look at. I had the reason why we had all those problems last week was basically my hard drive pooped to bed, so I had to erase my hard drive, reinstall everything. Luckily, I had backup files for everything, so it wasn't a big deal. But by doing so, I had to reinstall my operating system. Now all my permissions are set up funny. So now I'm going to ask for full disk access. No, I don't want that. Files and folders. No, I don't want that. Let's see. Zoom download folder, just got access to that. I'm supposed to be looking for share your screen, contacts, calendars. Sorry, guys. Photos. Maybe it's under cameras. No, that's not it. Input monitoring. No. Screen recording, I've got turned on now, but it won't do anything until I restart that, but I'm afraid that might be it, and that's going to stink. Require password. Anybody using a Mac know how to allow Zoom to share my screen? The login password has been set. I got that. I require password. Save again. Show message when screen is locked. Disable automatic login and use your Apple Watch to unlock. No, that's not it. File vault. I don't think I want file vault. Firewall and privacy. It can't be analytics and improvements. It can't be there. It literally says nothing about screen. This is not helpful. Let's try under advanced. Nope, nothing there. Nothing there. I put it on accessibility. That doesn't help. 1,000 folders. Zoom has access to that. So I'm thinking it might be the screen reporting thing, but I'm not sure about that. HomeKit with user availability. No. Nothing in there. Automation, nothing in there. Okay, hopefully that works. Let's see. Let's try one more time, see if it'll allow me to share. I might have to kill Zoom and open it back up, which is going to be a pain, but I think it keeps y'all here. I'm not sure how that works. Looks like it's working this time. Yes, it is working this time. I'll just do this. Sorry, folks, for taking so long. We are starting chapter 27, by the way. So, and actually 27 is really short. We've gotten a little bit behind, so we're gonna have to deal with that, but that's not super undoable. Okay, so it's allowing me to do this part, but it's not allowing me to do the other part. Oh, I know why. I'm not on Wi-Fi. Okay. Now it should be able to do it. Okay. So we'll start off with chapter 27 by letting you guys know that we've known about, as a society, we've known about magnetism for a long time, literally hundreds, maybe even millennia BCE, before the Common Era. Again, we're using the BCE, which is the modern way, as opposed to BC and AD. We use BCE and CE, before the Common Era and after the Common Era. But there is something that would bother you, that it might be religiously motivated, and it sort of is, in that specifically not everybody recognizes the birth of Jesus as Christ. So the BCE might not necessarily be acceptable for every race, creed, religion to use. Plus, we also know that he wasn't born on the year they thought he was. It was more like 4 BCE, or excuse me, I think it was 4 years in the Common Era that happened. So it's not correct historically either. So now we use the Common Era and before the Common Era. So anyways, we're using that, but we're talking about magnetism being found in a place which is basically modern day Turkey. They call it Asia Minor, but there was a place there called Magnesia, and rocks from there were known to do weird things like stick together or attract one another from a distance and stuff like that. So that's where we got the name magnetism from. And that is a major thing in physics and science, is there seems to be another force that we haven't addressed yet. So what's that force is we've already learned about gravitational force. We learned about that in like chapter 6 of 241, and we found that force was proportional to the product of the masses of two bodies. So any two bodies that have mass will be attracted to each other, never repulsive, by the way, and inversely proportional to the square of the distance between them. And the constant of proportionality, at least in newtons, turns out to be a really small number, 0 point followed by 10 zeros and then 667. So it's a teeny number. We also found Coulomb's law, which turns out to be the force that we probably interact with most. So like when I go to push on something, it's an electric force that keeps my hand from penetrating the actual thing I'm pushing. The electric force keeping the electrons from invading other atoms or even the nucleus of my atoms, and keeps my atoms from penetrating the material or the object's atoms and nucleus that I'm pushing. So the electric force is the one that you deal with most frequently in that sense. And that turned out to be a force that was proportional to the product of the charges, okay, not the masses, but the charges in coulombs. And it could be repulsive or attractive. So like charges repel, unlike charges attract, and it was inversely proportional to the square of the distance between them. But the kicker was that the constant proportionality, at least in newtons, turned out to be 9 times 10 to the 9th, essentially. So 9 billion, which is huge. Remember, the other one was 0.100667, and the Coulomb's law one was 9 billion. So that's huge. Well, it turns out that there is yet another force, and both of the first two forces, like this one, act at a distance. So we've actually since then created the idea of fields and all that good stuff. But lo and behold, we're going to find out that the actual force again is in some sense inversely proportional to the square of the distance between them. Okay, so it is actually something related to a distance squared in the bottom or in the denominator. So it is a force that in some sense falls off like 1 over r squared. And I'm saying that with a lot of hemming and hawing, specifically because it turns out you can't just have a one particular type of magnetic field. It turns out all magnetic fields come with a north and a south pole of the magnetic field, and then the field lines, in fact, always make complete circles, except when they're in transition from disappearing or to appearing, or from appearing to disappearing. So that's something that's kind of interesting. But we did know, for instance, that you can take rocks, and sometimes a rock from magnesia will stick to another rock. And then sometimes you can take one of those rocks and just turn it around a little bit, and then it'll repel the other rock. So eventually what we figured out is it's sort of like you can take this material that these rocks are made out of and just make straight iron. In fact, is what it turns out to be. You can take just straight iron, and if it's developed in the right way, it will actually have magnetism associated with it. And you can make like a bar magnet, and one end would be the north pole of the magnet, and then one end would be the south pole of the magnet. But it turns out magically, if I cut that in half, I don't get a north pole standing by itself and a south pole standing by itself. It turns out that now I've got a north pole and a south pole, and then a north pole and a south pole again. So it splits that up, and you keep doing that until either it becomes so small that it no longer has any magnetic properties, or it just continues to cut in half and always make a north and a south pole. Now we're constantly still looking for an isolated north pole around or an isolated south pole around. That's called a magnetic monopole. And if we ever found it, somebody definitely would win the Nobel Prize for it. But the neat thing is, like when we covered Gauss's law, we had Gauss's law said the closed integral of E dot dA, that was the electric flux leaving any closed surface. So you imagine an object, a surface that has a clear inside and outside. So for instance, a t-shirt sleeve does not work, right? You'd have to put end caps on the t-shirt sleeve for it to work, because then it'd have a clear inside and outside. But you take any shape that has a clear inside and outside, and the electric flux leaving that closed surface is equal to the charge enclosed divided by epsilon naught. Well, it turns out you get a similar law for magnetism, and it's the magnetic flux, the closed integral of B dot dA. Notice I said B. B is the symbol we use for the magnetic field here. So the closed integral of B dot dA is the magnetic flux. And if you take that over any closed surface, it turns out it's always going to be zero, because every line that goes out through the surface will loop back and come back in through the surface. That's what we mean by you're never going to find an isolated, piece of magnetic field line that doesn't have a closed loop, unless it's in transition from being there to dying, or from not being there, to being there. So yeah, you might for an instant in time see a magnetic field stop to exist. And what I'm referring to there is just sort of giving you a little caveat that allows you to understand, if we look at actual images of the sun and the sun's surface with a really good telescope and the right filters, you can see giant loops of flames and plasma looking stuff, and they're almost always closed loops, but sometimes they're not. And that's what I mean by sometimes the loops aren't closed. And that's more a matter of the basically the magnetic field sort of breaking, or maybe the flow of particles not going completely around the curl or anything like that. But a big idea is, in physics and science in general, if we ever see closed loops of stuff that's potentially charged, the first thing we think about is magnetism. Whereas if we see straight lines emanating from things, we think of electricity. And if we think of straight lines of very weak forces going towards one another, we think of gravity. So that's sort of the big picture of what magnetism is. And it turns out on the microscopic level, we can make some sense of it, but we're not that great about it. Like, we still, if you look at a middle school, sorry, I just changed subjects there, but I thought this is a better example with what I was talking about. So if you look at a middle school or a high school textbook, it will definitely tell you, why the Earth has a magnetic field, and they'll say it's the dynamo effect. And yeah, we got a name for it, but we don't really understand it that well, to be honest with you. So what we do know is that, according to Maxwell's equations, electromagnetic radiation can be created, and electric fields and magnetic fields can be created. And what creates electric fields is charges, and what creates magnetic fields in general we think of as currents. But it turns out that magnetic fields can also be created by changing electric fields. Okay, so, and that's what ultimately Maxwell did to fix Ampere's law. As it turns out, Ampere's law is not quite complete. Ampere's law says the closed integral of B dot dl, which you guys haven't learned yet, is equal to mu zero times I enclosed. It's sort of like Gauss's law, but instead of doing a closed surface, it just does it on a closed loop. But it turns out it's missing a term on the end, and that term is what we later termed the displacement current. But basically what it is a current can create a magnetic field. So a current is, charges moving in a given direction. So that's one way we could create a magnetic field. But we could also create a magnetic field by electric fields changing. So in that case, you could have some charges creating electric fields, and if they're changing, they're going to create a magnetic field as well. So with that in mind, you say, okay, well, what we do know about the Earth is that it's solid. It's got this hard outer layer, and it goes into a magma and all this stuff. But we know there's an inner core, and there's a core, and the innermost part of the core, based on our models and conditions that we can make here on the surface of the Earth that match the conditions deep within the center of the Earth, suggests that inside of that outer core is a solid inner core, and outside is a molten liquid outer core. That molten liquid outer core is so hot that and being a liquid, it allows free charges to move around. And those free charges are what we think, and the fact that they're moving around because the Earth's rotating, we think that is what causes our magnetic field. But again, it doesn't make complete sense, because the Earth rotates right around this rotation axis, whereas the magnetic field isn't really aligned with that axis of rotation that well, as we'll see in a second. So we don't really understand that perfectly or that well exactly why the Earth has a magnetic field. But in terms of thinking of ideas about whether we're right or not, it being related to the charge of free charges inside the surface, inside the magma, and Earth's rotation. We do know that Venus, which is about the same size Earth, I want to say the diameter is like 92%, 95% that of the Earth. And it turns out planets' internal temperature is really mostly dependent on the radius. So if two planets are comparable in radius, then they'll have comparable temperatures. That's the biggest indicator. So we think Venus has a fairly hot inner part, and in fact, it's probably likely that it does have some molten inner part or outer part of its core. I'm not a planetary astronomer, so I haven't kept up on that. They might know more than that nowadays, but what you would think is because they're about the same size, you'd expect them to have the same inner temperatures and made essentially the same materials. There's a few elements that weren't quite available to Venus that were available. I mean, yeah, Venus that weren't available to that were available to us. But generally speaking, the nickel and iron should definitely be there. So Venus probably has this molten core, which means it has access to those charges. But here's the weird thing. Venus has a very, very weak, maybe even slightly non-existent magnetic field. And we know that Venus actually rotates very, very, very slowly. In fact, it rotates backwards, and its year is actually longer or is actually shorter than its day. In other words, it takes more time to rotate once on its axis than it does to revolve around the sun. So that very slow rate tells us we're probably right about the two things that matter as to whether a planet can create a magnetic field. One, does it have a molten core, which would provide free charges? And two, does it rotate somewhat rapidly so that we can have these charges sort of accelerating around and making a magnetic field? Okay. So I'll draw a picture of the magnetic field in a second, but I just wanted to get that through to you. Now, molecularly, if we talk about these chunks of magnesia rocks, say, and we want to understand why exactly do they have magnetic fields, it turns out that you can sort of think of every magnetic field source as like a little loop of wire. In other words, take not literally a loop of wire, but imagine some charged particles moving around in a flat loop, say. That sort of sounds a little bit what we thought electrons did around the nucleus. So one little electron moving around the nucleus is sort of doing the same thing as making a current loop, because obviously an electron has a charge, and the charge per unit time is the current. So if you imagine it that way, you can then take the current, the charge per unit time, multiply that by the cross-sectional area of that loop, that area right there, and that actually gives you a magnetic moment. And it turns out that some atoms and molecules have better, stronger versions of that magnetic moment. And when they're at the molten state, they're sort of random, because the high temperature of a molten state causes the molecules and atoms to jiggle around real fast. But as you cool them, they sort of get in little groups, and you'll find big patches of groups where all the little magnetic monopoles line up, meaning all the, not monopoles, excuse me, magnetic dipoles, all the little magnetic dipoles all line up sort of parallel, if you will. Okay. And those are what we call neighborhoods. And it turns out if you get enough of those, or if you get the material saturated enough with that type of molecule or atom alignment, then you get a much stronger magnetism coming from the material. So one way you can do that is get something to molten hot and then submerge it in a magnetic field and then cool it off, because in the magnetic field, basically all the atoms and molecules are compelled to align to each other parallel. Okay, so it'll make those little neighborhoods. And the more of those little neighborhoods you have per atom or per number of atoms, the stronger the magnetism will be. And it turns out to make things a little more complicated, there's three types of magnetism. There's ferromagnetism, there's paramagnetism, and there's diamagnetism. So ferro, as you can tell, that comes from the Latin word for iron, ferrous. That's basically just like the paramagnetism, except it sticks a lot easier. And it's pretty much just nickel, I think cobalt, and some and iron, and some alloys of those elements that are really ferrous. All the other ones are essentially non-magnetic, or they're paramagnetic or diamagnetic. So in the Ferris setup, what I just said happens. And then when the magnetic field disappears, they stay in that spot. So they stay all aligned. That's a ferromagnetic material. However, if you do that same thing with a paramagnetic material, all the atoms and molecules will try to align as best they can. They align parallel to the magnetic field. But as soon as you let go of the magnetic field, they sort of break apart and the magnetism disappears. So it's a lot less likely to have them have a lasting magnetic field. And then the diamagnetism is really weird in that if you have a magnetic field, say pointing to my right, normally in paramagnetic and ferromagnetic, the magnetic dipoles will all align to my right as well, pointing the same direction. Well, diamagnetism, no, they line up backwards. But just like paramagnetism, once you take them out of the magnetic field, they more or less randomly orient, so they don't have any more magnetism left with them. Ferromagnetism even shows something called hysteresis, where it has a memory of where it's been. So it can, when you go through any sort of closed loop in the magnetic field as a function of time, that closed loop's not necessarily guaranteed to be closed. You can start at this particular time with this particular magnetic field that it's being submerged in, and this particular magnetic field that it's exhibiting, and it'll go up like this and then die off. But then when it comes back, it doesn't necessarily hit that point because it sort of remembers where it was. You can read about this in your book, but that's basically the basics of magnetism. That's the conceptual stuff that you need to understand. And like I said, if you were into material science or electrodynamics or many other fields within science and materials and geology and stuff like that, this might be an area of interest to you. But I just want to give you a rough rundown. Now what I want to do is I'm going to show you ways to make a magnetic field, and then I'm going to show you what the magnetic fields look like. Specifically, I'm going to touch on the magnetic field for the Earth. So right here, I'm going to share screen. And it turns out if you imagine the Earth as a sphere, wow, I draw a good circle, don't I? Just joking. Okay, so what we know as the Earth is a sphere is that it has a axis of rotation that's tilted, say, or you could say the equator is tilted at an angle of, say, whoa, didn't mean to steal that. The equator is tilted, dang it, keeps doing that. At an angle of 23.5 degrees, roughly. Okay. Now, it turns out that if, let's say this is our East Coast and Florida's right now. Well, actually, Florida can't be that low. But let's say this is Boston area, North Carolina, Florida, Texas, Yucatan Peninsula, so on and so forth, South America, all down there like that. This is California over here. And then there's this country called Canada up there, and there's this huge body of water right there. Well, it turns out that acts like our north magnetic pole. And I'll say magnetic North Pole, but I'm going to put a big caveat on that. So we call that the magnetic North Pole, but here's the weird part. In reality, what's going on there is the Earth is acting as if it has a bar magnet inside of it. And in fact, the north end of a compass will point towards that end. So in fact, that end is a south end of a magnet, and this end is a north end of a magnet. Okay. Now, what do field lines look like from that? Well, here's my insensitive motto about magnetic field lines. B lines, magnetic field lines, are like, and I'm going to be a little funny here, but I apologize for anybody I offend. Field lines are like old people. And this is very much an American phenomenon. I'm not sure other countries have the same thing. They leave the north and enter the south. We were just talking about someone's grandmother living down in Florida, for instance, and that's a very typical life trajectory as people grow up somewhere up north, say, and then as they become older and they have more resources and they can do what they want, they move down south where it's warmer and you don't have to deal with, shoveling snow and stuff like that. So they leave the north and enter the south. So that tells you which way field lines go. So for instance, these field lines from here would go, that makes me so mad when it does that. Okay, these field lines would do like this. And in fact, they're pointing that way there, that way there, that way there, and in that way. And in fact, they don't stop. They go right through the middle of this metal. Similarly, there would be another one over here. And there's a bunch of them. And in fact, you've probably seen diagrams of what magnetic field lines look like around bar magnets plenty of times. So you probably have a sense of what their direction is. But that's the way our Earth acts. It acts as if that north and south pole of magnets are roughly located as I drew there. There's a place in northern Canada where that basically acts like our magnetic North Pole, which again is technically a south pole, but it moves about 10 kilometers per year. So it's moving right now as we speak. We don't fully understand why that's so, and we don't fully understand why it's not aligned parallel to our rotation axis, which is that red line there. So all that stuff is to be determined to some extent. But when we say the dynamo effect, that's not really an answer. That's just giving it a name. And I can't even remember if they say dynamo effect or effect. I think the proper word would be effect, but I do hate those two words. So I'm going to leave it up to someone in English to help you guys figure that out. So that's what our Earth's magnetic field looks like. And in fact, we've got angles of dip, basically. So for instance, some areas on the planet have the magnetic field pointing up from the ground. Other places on Earth have it pointing towards the ground. Other places have it but running parallel to the ground. And as you can tell, for instance, if you happen to be right up, let's say, I want to mark this with a red spot. If I happen to be right here, a magnetic compass is going to give me the absolute worst help in trying to find north, because it's actually going to make me go somewhat south, right? So that's the danger, and there's corrections for that. And as long as you stay away from, upper northern Canada or the opposite end, which is out in the ocean somewhere, if you stay away from those areas, the magnetic compass can work pretty well. And they have maps to tell you how far it deviates at certain latitudes and all sorts of stuff like that. Of course, most of us are using GPS nowadays. And you can also, of course, use astronomy. The actual constellations can show you which way north and south is, because it turns out that directly above that south pole of a magnet that's inside of our Earth, well, not exactly above that, exactly above the real rotational North Pole, very, very close to it, within a degree or so, is a star called Polaris, and that's almost directly above our North Pole, our North Axis pole. So we can use that if we need to find north. That's a way better indicator, and it's never going to be off by more than a couple degrees, as long as you can find north. And we can use GPS, which works quite well with modern satellites and whatnot, but you can't pick up satellites everywhere. So any questions on how that magnetic field is oriented? So I will draw again another magnet, and it's going to be a bar magnet again, just so we can get an idea of what this magnetic field looks like. And as I said, if we were to cut this thing in two, it would not make a North Pole and a South Pole. It would make a North Pole, South Pole in the top half and a North Pole, South Pole in the bottom half. But the field lines from this, for instance, will go straight through the middle, and they'll actually get quite far out and then come back here like this. And this is their direction. And this one in here, for instance, would be like that. And they're actually supposed to get further apart the further out they are, because in fact, the density of the field lines, the number of field lines per unit area, is directly proportional to the strength. And B is actually weak out here. And the strongest part is actually directly inside the magnet and right near its poles. So you have another one. This one's probably going to be a little more realistic of a shape. Notice how far I went in drawing that one. This one, on the other hand, would be a lot closer like that. Again, so that's what the magnetic field lines, they should be way more symmetric than that, but you've probably seen this diagram before. We normally do a lab called Faraday's lab, and we'll actually lay, basically put a bar magnet, or you could do a solenoid. Solenoids turn out to make nice magnets as well. You can lay a bar magnet horizontally under a piece of plexiglass and then dump iron filings on the plexiglass, and they'll actually orient themselves along the field lines. And if you took the time to actually put out little compasses, so if I put a compass, say right here, what you'd see is that the compass north end, the one that's usually painted, would actually point that way there. It would point that way there, sort of tangent to the field lines, and it would point that way there. Actually, no, I said that backwards. Let's back up. I completely forgot to remind you to remember that the North Pole of a magnet points to the South Pole. And in fact, it would be, I can't believe I wrote that. Sorry, guys. Okay. So that's what your compass would do there. And I sat there and looked right at the stupid lines and the arrows and did it wrong anyways. So this is what the compass would actually orient itself like around this bar magnet. Because remember, the North Pole of the compass points towards the South Pole of a magnet. So right here, in fact, the compass would point that way. Well, magnets do create magnetic fields. That's one way we make it. So we say, how are magnetic fields created? Well, I already told you about how the atoms align to make up magnetic materials. So one is magnetic materials. And I said that's ferromagnetic, paramagnetic, and diamagnetic. Okay. But it turns out too that current can create them. Okay. So let's start talking about that. So a current in a wire creates a magnetic field. So now that you have this understanding of how magnetic field lines go and stuff like that, I'll say, let's imagine a current carrying wire. Okay. And let's imagine that the current is actually going up. That's the current I. And now let's imagine a plane perpendicular to that. In other words, the wire is in fact perpendicular to this plane. And in fact, goes through it like that. Okay. Now it turns out I should have drawn this table a little wider, so I'm going to draw it over here then. Okay, and now I'm in the center of the table. That makes it feel a little better. Okay. So if you take and grab this wire with your right hand, such that your right thumb points in the direction of the current. Okay, that's a terrible hand. But if you grab that wire with your thumb laying along the wire and pointing in the direction of the current, and then you curl your right fingers around that wire, that is the direction of the magnetic field. So if I go to the right, the magnetic field will point that way. If I go behind it, which is right here, the magnetic field will go to the left. If I go to the left of it, the magnetic field, let's say, is right here, that's going to come out at us. And if I go in front of it, it's going to go to the right. So what that means is if I put a compass right here, the compass is going to point that way. If I put a compass right here, the compass is going to point that way. Compass is going to point this way. Compass is going to point this way, and these arrows are getting too small to see now. That's not helpful. So the compass is going to go that way. So in fact, that's actually what is created is a magnetic field. And in fact, it actually has no components parallel to the wire. The magnetic field B is actually perpendicular to the current direction. If we were to assume current has a vector type quantity, in other words, the vector for current would be represented by that little blue arrow I drew. So the magnetic field is actually perpendicular to the current, and it's given by the right hand rule. So first off, I'm going to get rid of that hand because that's just scaring me. But anyways, that is the first right hand rule you run across in this semester. Okay. I will give you a hint that when you learned about the cross product in trigonometry, they gave you a right hand rule. And in fact, all of these right hand rules are a result of a cross product. So that's why we're having so many right hand rules in magnetism. So now I'm gonna go back here, fix this, bada bing, bada boom. Go back here, fix this. Okay. So I'm trying to actually show the magnetic field in the back a little more clearly. It points to the left, okay? And that's actually behind the wire. Okay, so everybody see how that goes, how the direction of the magnetic field lines are. So in fact, if I drew the magnetic field lines, I might draw them like, okay, let's say this is our wire again. Okay, let's cheat and use the self-correction mechanism. Let's do it again. Okay, let's do a current this way again. Okay, so what I'm saying is there exists a magnetic field that is tangential to this circle at all points. And this circle is in fact centered on the actual wire. So in other words, the center of the circle is supposed to be aligned with the wire. And here I'm getting OCD. So please bear with me while I have a little moment of psychological help. Okay. So, and in fact, that magnetic field strength B is proportional to 1 over R, which, if you remember, when we had an infinitely long wire of charge, we had a electric field that was inversely proportional to the distance, not the distance squared, but the distance. So this is just like that. Okay. So that's actually what the magnetic field looks like. I should actually put this as the center of the circle, but it's not letting me do that now because it's being a butthole. But anyways, maybe I can do it with this. Nope, it's not letting me select the thing. But anyways, yeah, that should be the center of the circle. And I think y'all can see well enough from that. So that's another way that we can actually create a magnetic field. We can use magnetic materials, and magnetic materials can be ferromagnetic, paramagnetic, or diamagnetic. And if they've been subjected to magnetic fields when they were going from the liquid state to the solid state, then they'll have some remembrance of that magnetic field. And in fact, we've even found that over the last 330 million years, the Earth has switched the polarity of its magnetic field 400 times. So that's roughly about every 8 to 900,000 years, our magnetic field of our Earth will flip, and it'll make, like right now, the south pole of our quote unquote bar magnet is close to our north pole. Somewhere in the next 900,000 years or so, we're probably going to have that become the north end of the bar magnet, and the south end will be the other end. We're not exactly sure, but we think that period when they're switching will be a period where there will be almost no magnetic field for the Earth. And that's a bit of a problem because the Earth's magnetic field actually protects us from charged particles that come from the sun. It's called the solar wind. And those things are what we call particle radiation, and they have the ability to cause cancers and stuff like that. But it turns out that the force acting on charged particles is not very normal. It again has another right-hand rule. And in fact, the force is, if you want to talk about the force due to a current carrying wire and a magnetic field, you could say that the force, why is it drawing dotted all of a sudden? Oh my gosh, I changed it to dotted. Oop, I don't even know how I did it. I did not want the lasso tool. I want this tool. Okay, there you go. All right, so if you want the force, it turns out that a force can be proportional to I times L. Use a vector that happens to be along the wire, okay, and pointing in the direction of the current. So in this case, this would be your L vector. And then you take a cross product of that with the magnetic field, and that gives you your force. You could also, in case your current carrying wire isn't straight, you could say DF is equal to IDL cross B, and that would allow you to determine the force as well. And then there's also another thing. If you actually just look at charged particles, it turns out that charged particles can be affected by magnetic fields, which is good because I just finished telling you about the solar wind. So those charged particles are affected by this. Basically, the force on a particle of charge Q moving with a velocity V has a force given by QV cross B. Now, I often just stop thinking about the current in the wire and just pretend it's positive charge particles moving in the same direction as the current, and I just use QV cross B. And that gives me at least the directions of the forces. So you can see right here how, if, for instance, I put let's say I put a positive particle right here, okay? What force and in what direction will that charged positive particle feel a force if it's sitting right there next to the wire? Pays close attention to my words. What force will that positive particle be subject to sitting right there next to the wire due to the magnetic field of the wire? Anyone? I will tell you that verbs are very relevant here. That positive particle is sitting there right next to the wire where the magnetic field, in fact, points into the screen. So what do you think the force on it is?
Positive.
Okay. It's actually, and this is me baiting you, so I apologize. I appreciate people taking time to actually answer. So thank you for that. I'm baiting you though, and everybody gets this wrong. The force would be 0 because of this. Everybody remember what that V was? I just said it. So if you don't, that's perfectly normal. You're probably thinking it's voltage, but it's Q, the charge of the particle, times V, the velocity of the particle, cross with B. So the fact that it's sitting there means that V is equal to 0. And that V being equal to 0 means there's no force. Now, if you have a current, let's say we have an XYZ coordinate system. And let's say this is X, this is Y, and this is Z. And we have a current carrying wire going this way. And let's say we have a positive particle with a velocity going this way. Now, which way, if any, will it be deflected?
The negative X direction.
Okay. So first we got to figure out, and I think you're right, by the way. First, we got to figure out what way the magnetic field's pointing. And since the current's going up, we know the magnetic field there is pointing into the page. Whoa. Sorry about that shakiness there. So that should be a circle. So yes, the magnetic field is actually pointing into the negative X direction. Okay. You might have been answering that, but you might have been answering the force. I actually asked for the force. So now what we do is we lay our hand with our pinky. We imagine basically our pinky bone running all the way to our wrist as one rod, like an axle. And if the charge is positive, then QV is the same direction as V. So I would lay my hand with that pinky rod parallel to the y-axis. And then I'm allowed to orient my palm any way I want to, but I need to do so such that I can curl my fingers of my right hand towards the direction of B. Well, the direction of B is into the page. So in fact, I've got to put my pinky rod to the right on the page. And then I've got to have my palm pointing towards the page so that my fingers can curl towards it. And in fact, what I'll see is I will get a force on the charged particle going up. So in this case, F is actually up. It's in the positive Z direction. So a big fraction of this chapter is understanding these right-hand rules. If you wanted to know the force on a current carrying wire, then you use IDL cross B. So let's say we've got a magnetic field.
Wait, so if you were to like shoot an electron at a wire, the electron would start following the current of the wire, almost like a Bernoulli effect.
Okay, so let's see. If I said, let's put a negative charge to answer your question. Let's put a negative charge right here. And let's say its velocity is going this way. And I will make sure we understand that this corresponds to that guy. Okay, so now I've got a negative charge going this way. Now, in that case, QV is in the negative X direction. And right out here in front, the magnetic field is actually in the positive Y direction. You see that? So QV, I'd have to put my hand, my pinky rod is going to point towards the wire along the positive X-axis, pointing in the direction of the negative X-axis. And then that acts like an axle. So my hand can do any of this kind of stuff at once. But because the magnetic field points to the right there, I have to turn my hand completely upside down like that. And my fingers can now curl to the right, which is the direction the magnetic field lines point. So in this case, it will actually cause a negative charge to go in the opposite direction. So this guy's going to go in the negative direction.
Wait, but doesn't the charge being negative flip the direction of?
Thank you. Yes, you're
V?
right. Yes, you're right. I forgot that it was negative. So QV shouldn't be that way. QV should be out to me, which makes it a lot more inconvenient to draw. But now you can see, yeah, it actually goes up. So yeah, you're exactly right. Good job. So
the current would just like pull an electron that's being fired at the wire along with the current. So like,
yeah,
like,
it looks like that's the conclusion. Crazy, huh? But that's because you're comparing electrons, which are charges, to currents. The magnetic field and the velocity direction of the particle, they're perpendicular to each other, but the currents can be quite parallel to the velocities. In that case, yeah, you're right. It's in the positive z direction. Cool for pointing that out. Thank you. I had not worked that far out yet. So yeah, that's cool. So yeah, the negative particle, because QV is that way, it's going to do this. My pinky axle is going to have to point out of the page towards me, and my thumb's going to have to stay up because my fingers can curl to the right direction of B, which is to the right on the page, only if my thumb is pointing up. So yeah, the force is ultimately going to be up for a negative particle headed towards the wire. So everybody get that? Crap. Okay, good. It's only 6:20. We go to 6:40. All right. So now I'm going to finish that example I started, which is imagine a magnetic field pointing into the page like this. We'll say it's uniform. Okay. And now let's say we have a current carrying wire that is this way. So current is going up. So according to F equals IL cross B, IL will point in the upwards direction. So we can imagine my hand going like that. So notice that axle that I talked about on my pinky is this guy right here. Okay. That's going to be right along I times L. So my pinky points that way, my pinky points that way. Now, the thing is with my hand like that, my palm can be in any position. I just have to treat that pinky bone as an axle, right? But what I need is my palm to point in the direction that allows my fingers of my right hand to point in the direction of B, which is into the page. So if I have my hand like this, I can't bend my fingers backwards. I hope y'all can see the little image of me good enough to see what I'm saying. So what I end up having to do is rotate my hand this way until my palm is facing the screen. And now my fingers can curl in the direction of B, which is into the page. And you see that the force is actually to the left. So in this case, the force on this wire will be that way. This was my IL, and of course B is into there. So that's some uses of the right-hand rule. Any questions on that? All right. So now that we seem to have that, what I'm going to do is show you one of the more difficult problems, which is this. Let's imagine I'm going to draw a coordinate system now. I'll draw it in red just because the coordinate system makes it easier to solve once you have it in place. So I'm going to say, here's my coordinate system. That's the positive x-axis, and I never remember that I can't continue with that easy drawing thing. Okay. To draw the actual letters. But
what I'm going to do now is put the x-axis here. I'm going to put the y-axis here. And what I'm going to do is imagine a current carrying wire that comes up to this point. And of course, it just erases everything because God hates me. Okay. Okay. Now what I'm going to imagine is that this is going to make a circular arc right here, not a parabolic arc. Thank you for not helping with any of that. Ah, jerk. Okay. Let's give it another try. And I'm going to go ahead and say, don't that guy. I'm going to draw one a little smaller, so make it a little easier for me. And I know it's going to come back to 3, and I know it'll have to hit here. So I get it there. I get it there. I get it there. So the wire is going to come up and do that. And of course, I've turned the nice automatic fixing thing off at this time, so that doesn't help at all. And then, in fact, the wire is going to go, damn it, doing that. Ugh. The wire is going to go that way. Sorry about my harsh language there. All right, so the current in this is I, and it's going that way. Of course, it's also going that way, and that way. And what I'd like to know is what is F total on this wire if the magnetic field, I'm going to actually say, is pointing out of the page, and it's a uniform magnetic field. And its magnitude is just B. So in other words, we're doing it quite theoretical, so it'll come out with answers that'll be valid for all B and I. Okay. So what we have is, for a solution, we know that F is equal to the integral of dF, which equals the integral of I dL cross B. Okay. So if you examine this first part right here, part 1, and then the second part, part 2, what you'll see is basically F on part 1, IDL would point up, B points out, so it'll be to the right. And it's equal to, let's call this distance A. So it'll be B times I times A, and F part 2, dang it, will be to the left, and that will be equal to B times A times I as well. So those two forces are going to cancel out. This part right here, of course, has a radius R, though, and we're going to make use of that. We're assuming we know R. I just didn't draw it in earlier. So what I know is part 1 and part 2, those forces are going to cancel out. What you might think is that because the IDL is always going to be tangential to that curve, you'll see that, in fact, it's going to have a component that is radially outward. That means it's got an X component and a Y component. And the X component points to the right for the right half and points to the left for the left half. So you don't expect this to have any surviving X component, but you do expect it to have a surviving Y component. But this calculus mechanism here is going to show us how. So I'm going to go ahead and write down that DL is going to be, what I do is I imagine a line right here, and that's an angle theta. And then I allow that angle theta to change by an amount d theta. Then this little distance right here becomes r d theta. And technically, I'd make that infinitesimally small, of course, but technically it should point in that sort of direction. In other words, it's tangential at the beginning because the d theta is really, really small. So there's very little difference between the r there and the r at the front point. Well, that r is the very definition of what we call the r hat vector, which is a function of theta. Okay. Actually, it's not the r hat vector, excuse me. It's the theta hat vector. I was thinking ahead there. That's actually the very definition of the theta hat vector from cylindrical coordinates, which is what we're sort of looking at here. So what I'm going to say is DL has a length r d theta. But it points in the theta hat direction. And since it's a hat, it's a unit vector, so that's okay. But I haven't really given you all the details about theta hat. So I'm going to show you it right now and work that out. And just know that whenever you're integrating or differentiating, you can't use theta hats and r hats. You can use I hats, j hats, and k hats, and that's it, because otherwise you're going to have to integrate them. So let's imagine our same coordinate system that we had up there. This is our x, this is our y, and let's imagine a point in space here that is, let's say it's a distance r away, and it's up an angle theta. At that point in space, in cylindrical coordinates, there exists a unit vector, which I'm going to draw in green, that points radially outward, and it's called r hat. And it actually is a function of theta, and it might even be a function of r, but it's a unit long. That's the key thing. And then perpendicular to that vector is a vector called theta hat. And that's a function of theta, and it's a unit vector as well. So those vectors just exist. From that, I can decide exactly what this vector is, because that angle right there is theta. So I can say that r hat is going to be equal to, notice the x component is just cosine theta. If I put an r in there, then that would make it have a length of r times cosine theta. And then the length of the other one would be r times sine theta. And then when you take the sum of the squares of those, you get r. I just want one. So I'm just going to say it's cosine theta I hat plus sine theta j hat. And if you check the length of that vector, it's the square root of cosine squared theta plus sine squared theta, which is, of course, just the square root of 1, which is just 1. So it is a unit vector, right? Now, if we look back at this, I think you can see that this angle right here is theta as well. So we can get that theta hat is going to be equal to, again, using the same argument that I don't want an r in there, I can see that the x component is going to be negative sine theta I hat, and then the y component is going to be cosine theta times j hat. And that is exactly what r hat and theta hat are. And in fact, you can do this for spherical coordinates, and this will help you in your dynamics class when you're talking about the omega cross r, or the centripetal force and all that good stuff, and the what's that other one? Dang it, can't remember the name of it. Anyways, the force that you have, basically the Coriolis force, excuse me. So that's where that Coriolis force comes from. When you actually work out what the r vector is in spherical coordinates, and you consider a reference frame that's rotating, when you take the derivatives of all these components, just putting them in terms of i's and j's, you end up getting the terms that represent the centrifugal, quote unquote, centripetal force, and also the term representing as the Coriolis force. and you just see that they're actually just part of the acceleration. They're not real forces. So anyways, we have that. And you might also notice that d r hat over d theta is actually equal to theta hat. So that's a nice way to remember it if you ever want to derive it yourself. So now I know that this is going to be, so going back to our solution. So dl is going to be r d theta times theta hat, which is in fact negative sine theta I hat plus cosine theta j hat. So I have, in fact, my dl, and my b is going to be actually out of the board. Notice your coordinate system has to be right-handed, so I hat cross j hat must give me k hat, and that means b is actually pointing out of the page just like k hat. So b is just going to be b times k hat. So now I can say f is equal to the integral of I, the current, times r. Actually, let's back up. Let's say negative r sine theta d theta I hat plus r cosine theta d theta j hat. That's what my dl vector is. And that's going to cross with b times k hat. Okay. So you can do the individual cross products and everything, but really it just helps you to know that I hat cross j hat is equal to k hat, and I hat cross k hat, for instance, I hat cross k hat just gives me negative j hat, and j hat cross k hat. So j hat cross k hat gives me I hat. Okay, so that's the way I can actually work this. I see the I, the b, and the r are all constant. So I'm going to say b times I times r comes out in front. And I'm going to get the integral of, now I have to do my cross product, which is going to be sine theta d theta and then that's I hat cross k hat and times a negative, plus I'm going to have a cosine theta d theta, and then that's going to be a j hat cross k hat. Okay. So I get b I r times the integral of I hat cross k hat. That means basically negative j hat. So that's going to become positive sine theta d theta j hat. And j hat cross k hat is going to give me I hat. So that's going to be cosine theta d theta I hat. Okay, and I'm going to integrate from theta equals 0 to pi over 2. Now from symmetry, remember from symmetry, we already argued that the x components should cancel out. And sure enough, the derivative of sine is cosine. So the integral of cosine is sine. So this part just becomes b times I times r times the sine of pi over 2 minus the sine of 0. Well, the sine of pi over 2 sine of pi, it is pi over 2, right? Let's see, 0. Oh, no, it's supposed to be pi. Stupid me. Scratch that, everybody. This is supposed to be pi. The long way to erase. There you go, just pi. So this is going to be with the integral BIR times sine of pi minus the sine of 0, which is just 0, which is what we expected. Now, the derivative of negative cosine is sine, so the integral of sine is negative cosine. So I'm going to get BIR times negative cosine theta evaluated from 0 to pi in the j hat direction. Now, the cosine of pi, of course, the cosine of pi is -1. So I get BIR times negative of -1, and then minus the negative of the cosine of 0 is 1. So I get 1 minus -1, so that's 1 plus 1 is 2. So I get 2 BIR in the j hat direction. And that's it. That's the entire force. And we finished just in the nick of time. Any questions on that? Like I said, everybody's free to go. You're going to be doing a lab using that QV cross B. And that's going to be the force on some electrons. And then the magnetic field is going to be perpendicular to that velocity. And therefore, it goes in a circle. So you can set that equal to mv squared over r. So that's really all you're doing for lab tonight is using that to work out what the charge to mass ratio of an electron is. But this should help you on that. And I will be putting up some more videos now that my hard drive's working. That'll hopefully little bit by little bit let you guys get caught back up by watching them as I assign them for our missed days. So I'll wait for the last of you to go. If anybody has any questions, I'll be here. Other than that, you're free to go. AJ, do you have any questions? You can chat if you'd like. You might not have your speaker working. All right, he might have been disconnected. I'm going to go ahead and let you guys go. So keep an eye out for your emails in case I make more videos for you guys. Have a good one.